Thank you very much for the introduction, and good afternoon, everyone. It's an honor to be the last speaker of today and this session. So for that, I will try to be brief so everyone can prepare for the ceremonial dinner that's later. And as it was mentioned, my topic was the Beremin parameter determination for 15KH2MFAA steel for standard and subsized specimens. And the reason for this was that this work was a part of the Fractasus project, which had an aim of evaluating small specimens for use in fracture mechanics evaluations. This project was divided into multiple work packages, and this work was part of work package 4, which was a purely simulational or numerical work package that supported the measurements done in work package 3. And my task was concentrated on the evaluation of brittle fracture, as the ductile to brittle transition is a really important phenomenon, especially in nuclear power plants, and because of irradiation embrittlement, and if there is something like a loss of coolant accident and cold water is injected into the system, then it will quickly bring the temperature down, and it shouldn't exceed the brittle fracture temperature. And the popular and very well used method was developed by Beremin in 1983, which is based on the Weibull distribution. And with this method, the theoretical T0 temperature can be calculated. The use of subsized specimens is really important because there's a scarcity of specimens in surveillance programs in the nuclear power plants, and especially irradiated specimens. There is the possibility of artificial irradiation, but it's expensive, time-consuming, and there is a limit to the capacity for it. And in this work, compact tensile specimens were used, both the normal 1T and the mini CT. And 3 reactor pressure vessel steels were analyzed in total, as you can see there. First, I would like to talk about the finite element model. It was an ACE model for both the mini CT and the normal CT, and it was done with J-integral calculation in mind. So you can see the circular finite element mesh at the crack front, and the J-integral was calculated first in the program, and then with a standard evaluation according to ASTM E1921. And they were validated with both experimental results and between partners. And besides the J-integral values, most important characteristics of this test were validated between partners. So the load line displacement force curves, the stress fields, etc. The outline for the calculation can be seen here. A method had to be developed to calculate Weibull stresses, as MSc Mark was used by us in this project, but it in itself doesn't calculate Weibull stresses. So a Fortran or Python code was needed to do that. I will talk about a bit about it later. And there had to be a decision made about which tools were to be used for this work, and the necessary scripts had to be written. which were then validated, and there were some troubleshooting iterations. The equation devised by Beremin can be seen here, with the principal stress, a reference volume, the plastic volume of a concrete mesh element, and there is a limit from which the mesh element is considered in this equation, and all those considered elements are then summed, then the absolute is being taken, where n is the variable modulus for these statistics, and with these the failure of probability can be calculated using the calculated variable stresses and a normalization stress, and then this in itself can be used, but later an optimization was made as well, so it had to be correlated with the experimental results, and the experimental statistic probability of failure was calculated using range probability, where n is the total number of specimens for a select material and the temperature, and r is the index of that specimen if sorted in an increasing order. And it's important to note that these two parameters, the m and the sigma u, are dependent on temperature and on the select material. So in the end, MSC mark was used for the finite element calculation. Excel was used for stress intensity factor calculation because there was already a tool available with which it was easier to do than to write a new script, a new Python script. A Python script was developed for the variable stress calculation. It had the advantage of easier data handling, and it could be run in tandem independently of the finite element simulations, because if Fortran were to be used, then it had to have been run with the finite element simulations. So these codes were developed in-house and validated and verified by our partners and with known results. So this is a little diagram for the tool chain. The left side we have MSC mark, and from that the load light displacement and the force from the simulations were brought into Excel, in which the stress intensity factor was calculated and the J integrals, and then every input was then taken into the Python code. And then the two variable parameters were optimized. So the modulus M and the normalization stress sigma u method had to be decided on. In the end, the linear regression and maximum likelihood method was used as well, and it had similar results for 15KH2MFAA, and there were multiple iterations and sensitivity evaluations were done for the use of string correction. In the end, it was not used, but it was taken into consideration. The element selection criteria, if an element is to be selected into the calculation based on the plastic strain, the stress, or the triactivity, or the combinations of these. But in the end, plastic strain criteria was used, and the measurements were censored according to this equation coming from the same standard. On the finite element side of things, the load increments and convergence criteria were analyzed as well, and different data handling methods were analyzed in Python. Here you can see some examples of the parameter optimization results, where with orange you can see the measurements, and with blue you can see the simulations, and with the red line shows where the censoring is cut off. But it's important to note that the rank probability is not influenced by the censoring, so it has to be still taken into consideration with the rank probability. And as you can see here, for these four temperatures and materials, all of these were mini-CTs. The agreement between the simulations and the measurements was quite good. And there was some simultaneous optimization as well. The idea was that even though the variable modulus and the sigma u is dependent on temperature and the material, it shouldn't vary widely between temperatures that are close together. And the simultaneous optimization were in 3 temperatures. As you can see, the agreement will be minus 110 degrees Celsius. Measurements were not so great, and all of these 3 were optimized at the same time. So it was left out, and so we can see here that leaving that out, we obtain a good agreement even with a simultaneous optimization. And here you can see some results in which the code itself converged. Parameter values were obtained, but the agreement between the measurements and the simulation is basically non-existent. It can be due to a high degree of plasticity, where a brittle fracture cleavage was not necessarily the cause of fracture, but it's still an open question. And as you can see here in the summarization table, the green values are those where parameters were obtained, and there was a good agreement between the measurements and the simulations. But with the red ones, those are still optimized values, but invalid due to having a really bad agreement with the measurements. And that's most of the material and temperature combination. So in summary, the possibility of a T0 calculation were or it was obtained due to good agreement with the optimization for the 15KH2MFAA on 2 temperatures, and we have a verified and validated tool that can be used to determine variable stresses. And so the Beremin model works with the tool. There are some sort of uncertainties for the optimization side of things, as so here there are some questions why these optimal values were not good for the agreement, and why some combinations there were no optimized values. So for the future, the exact reason of the discrepancies can be found. Because of the scope of the work, the optimization of the code was not done, so an optimization can be done. The routine can be shortened. More can be integrated into a Python script instead of using X11 in between, and the whole process can be shortened using machine learning, which requires a great data set. And with that, thank you for your attention.